first, what we have talked about is, you know, adding acidic water, right? So all of these things basically making alcohol from a double bond, right? That's what I'm trying to summarize here. Making alcohol from alkene. Simplest reagent that you could use is to dump into the acidic water, even though they not physically mix them well, but let's say it would happen, then what's going to happen? Then protonations of double bonds make a carbocation, right? Once you see the carbocation, you shouldn't forget about the carbocation can be arranged. That's something that you've got to keep in mind. The carbocation is going to be captured by the water, then you are making alcohol. So that's one of the easiest way to make an alcohol in paper. In principle, it could happen, but it doesn't go well because of these two, water and organic molecule, they don't get mixed well. That's unfortunate. So that's the reason you need to have another reagent. But this one makes a molecule of nuclear products because of nucleophilic waters goes on the more substitute side. Another reagent for doing that hydration reaction is oxymercuration, demercuration. Mercury acetate is a soft electrophile that attacked by the pi electrons. You get these three-member ring intermediates. Mercury is pulling electron density from the carbons, and then more substituted carbon lose molecular density. So this more substituted side is going to be attacked by the nucleophile. In this solution, only nucleophile is the water. The water makes an attack from the opposite side, the trans or anti-attack, backside attack. Make the mercury goes one way, and then away from the water on the other side. Obviously, mercury has to go away. That's the second step. That's called the demercuration step. We do it with the sodium borohydride. Mercury replaced by the hydrogen, so you get alcohol, single OH. But that's a more technical product because OH is sitting on the more substituted carbon, right? Speaking of the adding water, there's another way, which is a hydroboration. BH3 is going to be added on double bonds, but as we discussed, it's a static reason. Smaller hydrogen goes to more substituted side, bigger BH2 goes to less substituted side, and this is syn addition because it's a very conservative mechanisms. Hydrogen and borons will be added on the same side. That's the way it is. BH2 will be replaced by the OH in the oxidation step. Second step, hydrogen peroxide and then hydroxide will replace BH2 with an OH. OH goes to the less substituted side, not the more substituted side like the molecule and the oxymercuration demercurations. So this is an anti-molecular product. Remember these reagents? Halogens in water. That's the halohydrogen reactions. In this case, bromohydrogen reactions. Bromine is electrophile. The pi electron makes an attack. You're going to make a very similar three-member ring intermediates. Bromine is going to be positively charged, so it's going to pull electron density for the carbon it bonds to, and the more substituted carbon lose more electron density, just same as before. And that more substituted carbon is get attacked by the solvent, which is the water, from the backside. So you got hydroxyl groups there, but bromohydrogen reaction, you got the bromine sitting in the next carbon, right? When you see that in trans relationship, OH on the more substituted side, and then halogen on the less substituted side, and the trans relationships, and this must be coming from the halohydrogen reactions. So this is still the mark of eco products. If you think about that, nucleophilic waters is sitting on the more substituted side. Now we learned another way of the making alcohol, but this one we have two hydroxyl groups. First, epoxidation happen with a peroxy acid. You make a cyclic epoxide. After protonating epoxide, you get this oxygen positively charged, full electron density from the carbon it bonds to, and the more substituted side, lose a molecular density. You can keep hearing the same thing over and over again. I hope that that's what you're going to remember later. That more substitutory carbon with the more electron deficiency, that's the one attacked by the water. So you got the OH on the less more substitutory side, that OH coming from the water, and less substitutory side, you got the OH, but that OH coming from the epoxide. So you got diol created, two hydroxyl groups, not one, two. But there's another way, which still that's why I think it's a macrobial product, because the nucleophile sitting on the more substitutory side. Another way is that you treat the double bonds with oxygen tetroxide, manganate, hold it dilute, then you're gonna get the two hydroxyl groups on the same side, and that is a cis diol. So all of these are alcohol. You added OH. Some with two, some with just one. Other one, not only adding alcohol, we actually adding halogen. You need to figure out what reagent does what. Not only the where things goes, but also the how they're going to look like, the stereochemistry, visual chemistry, choosing the right reagents. There's so many things here that can make you